Okay, so here we are back in GPS, the GNet Programming Studio, and here we will actually look at the race conditions that are detected by CodePeer in this Dining Philosophers program. So we're talking about the same source code as we had before, diningphilosophers.adb and so on, and we've run CodePeer and we've got the same sort of output. But now we're going to actually focus on the race conditions. And race conditions, you can see them in two different places. One, there's a separate window devoted strictly to race conditions. And also down here in the locations window, we have some information that's specific to race conditions. And actually, there's a third place, is that there are individual messages at particular lines that relate to race conditions. So what is a race condition? A race condition, as we've said, is when you have a global data object. In this case, CodePeer identified two global data objects, one called still eating, which is declared in the body of Dining Philosophers, and another one called counter, which is also declared in the same place. And then if we look at what sorts of operations are performed on these global variables, we'll see that on this one, we have a read and an update in the task type body of the task type person. And similarly, we have both a read and update in the busboy task, which is just a single task as opposed to a task type. So for this counter, it's only read by this task. So you might say, well, there's no problem. But in fact, this is a task type. And by its very nature, therefore, we can't read unprotected, unsynchronized global data because a given task type is typically being executed by multiple task objects simultaneously. Now, if we double click on this, it'll take us to a place where we are reading counter. And this is one of various places where we're reading counter. If we go back to where we were, let's go back to the race condition report. We see that reading counter is read in task type person. So again, here we are in task type person, and we see it's bumping this counter. If you remember from our discussion earlier, this is simply keeping track of how frequently we go around this loop. It doesn't have any particular importance to the algorithm as a whole, but it illustrates the kind of race condition that CodePeer can locate. So here is our variable. It's a global relative to this task type, and therefore it's not safe to do this kind of an operation on it because if you imagine there are two or more of these instances of the task type person running in parallel, you could imagine that one of them loads counter, and then the next one loads counter, and then one of them adds one, and the other one adds one, and then one of them stores the value, and then the other one stores the value. In this case, the total number of increments will only be one, because even though we've executed this statement twice, we've executed it in an interleave fashion, and the net effect is that both of them read the old value of counter before either had incremented. They both added one to that, and they both stored back the same value, which is only one more than the original counter. So anytime you have this kind of an operation, you have to be careful to be sure that that only one task at a time is doing it, or that it's some kind of a protected operation. And this is not. This is simply using the regular assignment and so on. So there's no special synchronization happening here. If this were an atomic object, we would still have a similar problem in that we could still have the same kind of interleaving. But from Ada's point of view, it's no longer erroneous. It's probably just wrong. And in some sense, this is distinguishing between low-level data races, as they're called, and higher-level logical race conditions. This is a logical race condition, even if counter is an atomic object, meaning that its loads and stores are indivisible. They won't be broken up in the middle. But it's still a logical race condition in the sense that we're not always going to add one for each time we execute this statement because of the interleaving I just described. So CodePeer is actually recognizing data races, which is a somewhat lower level problem. And if we added a atomic indicator on this object by saying with atomic or pragma atomic, it would no longer complain, but it might still represent a problem for your algorithm. So there are limits to what any tool can detect. But in the typical case where you just say, oh, let's just bump this counter, CodePeer will be quite effective at identifying such a problem. Okay, and so the other variable that we identified as being a problem was the still eating variable. And that one is not only referenced from reentrant task type code, it's also referenced from this busboy task. So we've really got two kinds of problems happening here. And if we look below, we can see where the actual individual messages come up, having to do with unprotected access of still eating. There's one here, another one here, and so on. And we can get to these points of access both through these messages down here. There are also messages here. So there are many different ways that we can get to the problematic shared uses. And you'll notice there's unprotected access and also unprotected shared access. And the difference here is that unprotected access is when you're referencing something from reentrant code, and that by itself is dangerous. And unprotected shared access means it's actually shared between two different bodies of code, two different task types, for example. And so that's a second kind of problem. And both of these are considered data races or race conditions in this sense. So we can look at the unprotected shared access from busboy, and sure enough, let's see. So I'm sorry, this is the one in the, let's see, go to here. Where is it? There it is, busboy. And sure enough, it's referencing still eating, it's assigning to still eating, and so on. And all of these are considered problematic, if you will, uses of this global variable. Again, still eating is also a global variable. It's declared a little higher, I think. There it is, still eating. So it doesn't have any kind of mention of being atomic. It's not placed safely within a protected object, for example. It's just sitting there as a plain old global variable, and so CodePeer is going to be complaining about the fact that we're referencing it from two different tasks, and in fact one of the references is from a task type, which right here, and down here is the other sort of task where we're referencing still eating. So we've got a number of different problems. Each one will be flagged as an error. And each one, here we have a read, here we have a write, and similarly up here we have both a read and a write, and these will all be identified as problems. So that gives you some feeling for the kinds of race conditions, some data races that CodePeer can identify. As mentioned, there are two ways you can find them. You can either look under this race conditions tab. There's the overview messages tab, but then there's the race condition tab, which is the one that we were just talking about here. By selecting the particular object that is shared potentially between multiple tasks, we find out what sorts of things are happening, and then we can click on one of these and it'll take us to that particular task or task type where the problematic reference is happening. And the second way to get at the particular problems is to look down here in the locations window, and the race condition messages appear both as individual messages underneath the particular file where they exist, and they also will have the appropriate color representing the medium or low warning level associated with that message, and you can click on these and go to the corresponding point in the program. Now we'll go back to our presentation to finish up our discussion of the advanced features of CodePeer.